Welcome, everyone. For today's prep, we're going to start to look at optimization. And a lot of this is going to be kind of things we've been doing with finding intervals of increase, decrease, and first and second derivatives. But we're going to actually see in this section, we're going to start to look at the first derivative test. And what the first derivative can be used for is, well, we already know it. We can use it to find what we call the critical numbers. But now we're going to see how we can use our first derivative to actually classify these critical numbers. And what we mean by classify is maximum or minimum. So we've looked at the definition of critical number before. So let's kind of review over that. So this is a number x equals c. So we say it's a critical number of some original function f if either the derivative is equal to 0 there, or the derivative is undefined there. And, well, this number also has to be in the domain of our original function as well. So why we're interested in these critical numbers is there's a result by Fermat, called Fermat's theorem here. And what it says is that if our function f has a local max or minimum at this number x equals c, then either one of those things has to happen. So either the derivative has to be 0 there, or the derivative is undefined there. So these critical numbers, our interpretation of these critical numbers, these are the possible locations. These are the only possible locations where our function could have a max or a min. So critical numbers. These are the only possible locations. Where f can have a max or min. But what this doesn't say is we're not necessarily guaranteed to have a max or min if these conditions are satisfied. So they're only the possible locations. So it's possible we have a critical number where it's not a max or min. So we want some way to be able to classify these. So the warning here is this doesn't necessarily guarantee that a critical number is definitely going to be a max or min. Okay, so it only tells us there's a possibility. All right, so let's just see some examples of graphs of what it looks like if the derivative is 0, what it looks like when the derivative does not exist. So when the derivative is 0, so in this first graph here, we have a local min at our number, x equals c. So we have a local minimum at x equals c here. And, this makes sense because if we're looking at that point, imagine if we were standing at that point, it's uphill in both directions. So that's a local minimum. And in this case, what's happening is the derivative at c is equal to 0. So when the derivative is 0, that means we have a horizontal tangent line. Graphically, what that looks like, though, is we kind of have this nice kind of smooth, rounded curve look to our minimum there. Now, in the next graph, we have another local minimum. So this is also what we have a local minimum on this graph at x equals c. But in this case, if we look around that point, well, imagine kind of standing there. If we were standing at that point on our graph, it's uphill in both directions, so it definitely is a local min. But in this case, we don't have a tangent line at that point, so the derivative is undefined. So this is where our graph kind of has a sharpness to it. Okay. Now, one other case that can happen is something like this. So just to give another example, at number x equals c here, if we're looking on the graph, this is neither a max nor a min. It's not a max, it's not a min, because it's not a minimum, because I can go uphill in one direction, but then I can go downhill in the other direction. So it's not really a max, it's not really a min. But in this case, we do have a horizontal tangent at x equals c. So this is a critical number because the derivative here is equal to 0. So all three of these graphs all have critical numbers at x equals c, but only the first two actually give us a minimum. The last one here, it's a critical number, but it's not a max or a min. So when we find these critical numbers, we need some way. We're not necessarily guaranteed to have a max or a min, so we need some way to actually test to see what's going on. And our test here is, well, we're going to learn two tests, but the first one we're going to use or look at is the first derivative test. And it's going to use our first derivative. And the nice thing about this first derivative test is it involves almost all the same work as finding the intervals of increase, decrease. So let's say we have a critical number x equals c. We're going to be working with continuous functions here. And if we have our sign chart for f prime, and we see that it changes signs from positive to negative at that critical number, well, then our function has a local max. And if f prime changes from minus to plus, well, then our function value there is a local min. And when we do this, when we do our first derivative test, the work here is basically find the intervals of increase, decrease. So we get to reuse a lot of our work here. Let's just explore why this makes sense. So let's suppose that we've found a critical number. So let's look at these first two graphs. And we can see that at x equals 2, we have a critical number here. So why is x equals 2 a critical number? Well, because in each of those cases, we have a horizontal tangent line. So we could draw our tangent line here, and then draw our tangent line here. And each of those is horizontal. Okay. So we definitely have a critical number at x equals c. Now in the first case here, this is an example of a local max at x equals 2. And in the second graph, this is an example of a local min at x equals 2, at our critical number. And what's happening? Well, if we think about what the sign chart for f prime would be in each of these cases, let's do a little sign chart for f prime. So we draw our x-axis, we plot our critical number, and then we think about what f prime is doing and what that's telling us about the original function f. So if we look at the function is increasing on the left-hand side, which means f prime is positive. And on the other side, the function is going down. So that means f is decreasing and f prime is negative on that side. So if we go from positive to negative, our graph is going to have this kind of look to it. So when we're doing our sign charts to get the intervals of increase, decrease, to kind of help remember what's going on at a critical number, it kind of helps to draw increase, flattens out, decrease, just to draw the shape of what the graph is going to look like to help remember what this first derivative test is saying. And then in this second graph over here, let's draw our x-axis. We got a critical number at x equals 2. And what's going on in this case? Well, if we were to be doing our sign chart, what we would have found is that our function's decreasing on the left-hand side. So decreasing, and all the derivative values there are negative. And then over on the right-hand side of our critical number, the function's moving back up. So all of our derivative values would have been positive. And so what the first derivative test says is when you switch from minus to plus, when f prime switches signs like this from minus to positive, well, really what's happening is your function is switching from decreasing to increasing, and you end up with a local min. So when you do the sign chart, you find the intervals of increase-decrease. To kind of classify that critical number, we'll just draw in the graph and see what it looks like. Now these last two, these also have critical numbers at x equals 2, because in each of these we have a horizontal tangent line at x equals 2. But each of these would be considered neither. It's not a max, it's not a min. So this critical number here at critical point at x equals 2, we have a horizontal tangent line, so it's definitely a critical point, a critical number there, but it's not a max, it's not a min. And what you would see on the sign chart, in the case of the first one here, what would our sign chart look like for f prime? So x equals 2 is our critical number on this graph. And if we were doing our sign chart, well, on the left-hand side, our function's increasing. So that means f is increasing and f prime is positive. And then on the other side, well, our function's still increasing, so it's still going up. So on the other side, it would be positive and increasing. So what we see here is there's no sign change. So if there's no sign change and you go from positive on one side to positive on the other side, well, then your graph is going to look something like this. And if we go to our other graph here, again, we have a critical number at x equals 2. So we plot that on our sign chart. And if we were trying to figure out the intervals of increase-decrease, what would we find for this graph? Well, if we go up to our left-hand side, it's moving down, so it's decreasing. So f would be decreasing, and then that means f prime would be negative on this side. And we see the same thing going on the other side. F prime would be negative, our function's decreasing, so our function's going down. So in this case, there's no sign change again, so this would be neither, not a max or a min. All right, so let's try an example. So let's look at example 1. So we're going to suppose that we have some function f, and we know its domain is everything except -3. So that'll be important for knowing the critical numbers. And then we also have information about its first derivative. So the first derivative is given right here. So it's x times x minus 1 squared times x plus 3 raised to the -3. And what we want to do is we want to find and classify all critical numbers of our original function f. So before we get going, we see a negative exponent, usually helpful to rewrite this as a fraction. So we're going to rewrite this as, we'll put the x times x minus 1 squared in the numerator, and then in the denominator we'll have our x plus 3 cubed. All right, so we're just rewriting this. So first step is we want to find our critical numbers. So we want to find them. And that's, when we've done this before, to get our critical numbers, we want to know where is the derivative either 0 or where is the derivative undefined. So those are the two possibilities for our critical numbers. And the nice thing about having a fraction is we can look at the numerator, set the numerator equal to 0 to get where this to get where this derivative is 0. And then we can set our denominator equal to 0 to figure out where it's undefined. Okay. So let's do that. So we'll do our numerator equal to 0, and then we'll do our denominator equal to 0. So when we set the numerator, we get x times x minus 1 squared equal to 0. And we can break that apart into the different factors. And when we have a factor like this that's being squared, the exponent isn't the thing that makes this equal to 0. It's the stuff inside the squared. That's what makes it 0. So the exponent really doesn't do anything here. So we can just set x minus 1 equal to 0, and then that gives us x equal to 1. Okay. So that's the critical numbers we're getting from our numerator. Now, what about the denominator? Well, same thing. We're going to set the denominator, x plus 3 cubed equal to 0. And since this cubed is around everything, the cube itself doesn't actually make this thing equal to 0. It's the stuff inside the cubed. That's what makes this 0. So if we set just that equal to 0 and solve, we get x equal to -3. Oops. And so what it looks like is we end up with 3 potential critical numbers. All right, so we found our critical numbers, and now we want to actually classify them. So that's the next step. So find is the first step, then classify them. And this is where we're going to do our sign chart for f prime. So this is basically finding the intervals of increase decrease. So let's see what this would look like. So we're going to do our sign chart. Plot the numbers that we found. So we got -3, 0, and 1. And again, that's splitting up our x-axis into kind of 4 different sections here. And then we want to figure out the sign of f prime on each of those intervals. So when we do this, let's write down each of our factors. So we've got x minus 1 squared, we've got x plus 3 cubed, and then we'll see what that tells us about f, and then ultimately f prime, and then ultimately f. And let's fill in our sign chart here. So starting with the easy one, the squared term is always going to be positive, so we can just go right across. Positive all the way. And then we can use test numbers, and I think we've done this sign chart before, actually. So we can use a test number, maybe like -4, plug it into the x factor here, and we get -4, so negative. And then this x factor is going to stay negative until we get to the root that we got from setting it equal to 0 and solving for x. So this one's going to stay negative. And then once we get to x equals 0, it's going to switch and be positive. Okay. Well then, for the other factor here, x plus 3, do a test number. So if we plug -4 in, we get -1 cubed, so negative. And again, this one, same kind of thing. It's a linear term, but we're cubing it. So it's an odd power, so it's going to start off negative here, and then once it gets to its root that we found from it, so -3, then it's going to switch signs. So it starts off negative, we get to the root, and then it's going to switch to positive. And then it's going to stay positive. And so if we fill in the rest of this, double negative is positive, which means the original function f is increasing on that first interval. Then for the next interval, we have a single negative, so that means the original function is decreasing there. And then for the last two, everything's positive, so that means f prime is positive and we're increasing. All right, so now classifying is just doing our intervals of increase, decrease. So now what we want to do is just interpret this sign chart. And we want to figure out, well, do we have a max or a min at each of these critical numbers? So if we're looking at x equals 1, what do we see? That's one critical number. But if we look, we go from positive to positive. So there's no change. So that means x equals 1 is neither. It's neither max nor min. It's not a max there, it's not a min. And that's because we don't have a sign change. So if we were going to try to graph what the original function would look like, it would look something like this, right around that critical number. All right, so that's x equals 1. What about x equals 0? Well, if we go to x equals 0, there we do see a sign change. And what's our sign change? We're going from negative to positive. So to help remember what the first derivative test says, draw in what the graph is going to look like. So we know it's going to be decreasing, then flatten out, and switch to increasing. So if we draw that shape, it looks like a min, and that's precisely what the first derivative test says. So at x equals 0, we have a local min. And that's because we do have a change, and we go from negative to positive. Now, what about x equals negative 3? So if we look at our sign chart, we do have a change in not concavity there. We do have a change in sign. So we go from positive to negative. So that would normally mean increase and then decrease. It would mean a maximum. But x equals 3 is not actually a critical number. So it's kind of tricky there. So x equals negative 3 is not actually a critical number because it's not in the domain of our original function. So even though if we're doing our sign chart, it looks like we have a critical, or it looks like we're going to have a max or min there, this is not actually a critical number. So it's not in the domain of our original function. So one of the things about critical numbers, if we go back to the definition, for critical numbers, it seems kind of small, but our function actually has to be defined there. So the critical number actually has to be in the domain of our function. So if it's not in the domain, then the point isn't on the graph. So you can't have a max or min on a point that's not there. But going back, when we do the sign chart for this one, that x equals negative 3 actually is important because even though our function's not defined at x equals negative 3, we can still switch from increasing to decreasing. So if we were doing our trying to find our intervals of increase, decrease, that x equals negative 3 is still important, but when we go to find and classify the critical numbers, we just got to be a little careful to check to see if things are actually in the domain. All right, so this one ran a little bit longer, so apologies. But we'll try a few more of these in class, so we'll see you then. Bye-bye.